Welcome back, everyone. This is Professor Herring. In this video, we're going to do some extra practice problems relating to standard enthalpies of formation and bond dissociation energies. Let's begin. So, as normal, pause the video, read over the question on your own, and try and solve it. Then resume and come back, and I'll walk you through a solution. Welcome back. So we want to know what's the standard enthalpy change of formation for strontium carbonate. Well, this is applying Hess's law to standard enthalpies of formation. And hopefully you noticed that you're not given a final reaction. And that's because you need to see that in order for us that you can figure out what it is on your own. We want to form strontium carbonate. Therefore, we must have strontium in its standard state, carbon in its standard state, and oxygen in its standard state. Okay? And let me rewrite this to give us a little bit more space. So we've got strontium in its standard state plus carbon. I'm just going to write S for solid. And then oxygen in its standard state. Those react to form strontium carbonate. Now, it's not balanced. We have one strontium, one carbon, but the wrong number of oxygens. We cannot change the value on the right. It must be 1. So we're going to end up with 3/2 oxygen on the left. And that's okay, because the definition is that we need to use elements in their standard states and form 1 mole of product. So, knowing that, we can take reaction A as is, because we want to have strontium on the left. Reaction B, we need to take and reverse in order to get strontium carbonate as our product. And then reaction C we can leave as is, because that's going to give us the carbon that we need. So our net reaction is going to be negative enthalpy for B plus A plus C. And you can rewrite all of them out, and you will indeed see that we get our desired reaction. So when we combine together the enthalpies, make sure that you're accounting for the change in sign for reaction B. We get negative 1220 kilojoules. All right, try this one on your own and come back when you're ready. Welcome back. So we want to know what's the enthalpy of reaction shown below. We're given the enthalpies of formation of 2 of our substances, and we know that the enthalpy of formation for hydrogen gas is going to be 0 because it's an element in its standard state. To find the enthalpy of reaction of the products, enthalpy of reaction, we need to sum up the enthalpies of formation of the products and subtract those of the reactants. So that's going to be 1 mole times the enthalpy of formation of our product, which is the methanol, minus 1 mole times the enthalpy of formation of the reactant, which is, this is an aldehyde, plus that of hydrogen gas, which is 0. You solve for that and you get negative 92.4 kilojoules. Here's a follow-up question. Based on the previous question, what would we expect to be the best estimate for the enthalpy for reaction 2 shown below? Pause the video, think about this, and come back when you're ready. Welcome back. So, What's the difference between these two reactions? It's only the states of matter here. And if we look at the enthalpies, the enthalpy of reaction for reaction number 1 is going to be our reactants going to form our products, and it's going to release the 92 kilojoules. What's the relationship in energy between the gas and the liquid? Well, gases are at a higher energy than liquids are. Remember, when we've talked about our energy, our heat curves, it takes energy to go from the liquid to the gas phase. And therefore, our gas phase is at higher energy. So our liquid is going to be below in energy, which means then that the net change is going to be a larger overall change relative to the first enthalpy, which means it's going to give off more energy and be the negative 130.6 kilojoules. Okay, let's try another problem. Pause the video and try this one on your own first. Welcome back. So we're given some bond dissociation energies for specific bonds. We want to know what's the enthalpy of reaction for the combustion of 1 mole of the substance shown below. What's the first step? Well, it's to write out the balanced chemical equation. After that, we need to write out the Lewis structures. Then we account for the number of each type of bond that is broken and formed. In our reactants, we have 1 carbon-hydrogen bond, single bond that is broken, and there are none that are formed. There's a net change of 1 that's broken. Carbon-carbon double bonds, there's 1, and none are formed. Carbon-oxygen single bonds, we have 1 right here, and there's none that are formed. Carbon-oxygen double bonds, there's none, but we form 6, 2 for each carbon dioxide. Oxygen-hydrogen single bonds, there is 1 that is broken right here, and there are 6 that are formed, 2 for each water. And that's a net of 5 being formed. For oxygen-oxygen double bonds, we have 4 that are broken, 1 for each oxygen molecule, and none that are formed, for a net of 4 broken. For carbon-hydrogen single bonds, we have 1, 2, 3, 4, 5 that are broken, and none that are formed, a net of 5 broken. So to find the enthalpy of reaction, we take the sum of the enthalpies of the bond dissociation energies of those that are broken minus the sum of those that are formed. Again, the reason for that is because in reality, we're summing together all of the steps, and the ones that are formed give off energy. And therefore, they end up being a negative value. So we have 1 carbon-carbon bond, 1 carbon-carbon double bond, 1 carbon-oxygen single bond, 4 oxygen-oxygen double bonds, and 5 carbon-oxygen or carbon-hydrogen single bonds that are broken. Then we're going to subtract the 6 carbon-oxygen double bonds and the 5 oxygen-hydrogen single bonds. We can then plug in those values and solve, and we get negative 17,044 kilojoules per mole. Okay, we've got, oh, excuse me, I've fallen into the trap. Did we solve for our final, that was the enthalpy of reaction, but did we solve for what we wanted? We want 1 mole of substance. So we take that enthalpy and divide by the coefficient in front of the substance we're solving for, which is 1. Okay, Last problem here. Given the following bond energies and heat of reaction for the process below, estimate the carbon-hydrogen bond energy. So this is a little bit different, but you can do it, I'm confident. Pause the video and try this on your own first. Welcome back. So you're given the balanced chemical equation. You should double check that it is indeed balanced, and it is. We need to draw out the Lewis structures. And then determine the bonds that are broken and formed. So we have a carbon-carbon double bond that is broken, 4 carbon-hydrogen single bonds that are broken, and 1 hydrogen-hydrogen single bond that is broken. We form 1 carbon-carbon single bond and 6 carbon-hydrogen single bonds. Our net then is that we break 1 carbon-carbon double bond and 1 hydrogen-hydrogen single bond, and we form 1 carbon-carbon single bond, and we form 2 carbon-hydrogen single bonds. Our enthalpy of reaction is going to be found by taking the sum of the bond dissociation energies of those broken minus the sum of those formed. We can then plug in our values. We know that we're going to use 1 carbon-carbon, 1 hydrogen-hydrogen, and we're going to form 1 carbon-carbon single and 2 carbon-hydrogen single bonds. We know that that's equal to negative 137 kilojoules per mole. When we plug in our values, we see that we're missing, again, we don't know the value of the carbon-hydrogen bond, we're trying to solve for it. So when you solve for it, we get that 702 kilojoules per mole minus 2 carbon-hydrogen bonds equals negative 137 kilojoules per mole, which means that for 2 bonds, it's 839, and a single bond is approximately 420 kilojoules per mole. That's it for this video. Thanks for watching. If you have questions, you can ask on Piazza and office hours or recitation. See you later.